So welcome back, and we are going to talk about methods now. So we talked about basically conditional statements, how to write programs by actually enumerating multiple statements within the main method. But we didn't really talk about what if we want to repeat the same set of statements, maybe parameterized for some values of local variables, multiple times. Like for instance, let's assume that we compute the average of a collection. We can implement an abstraction called a method, which, given a collection, returns the average of that collection. We don't have to implement the code to actually compute the average in every single occurrence of the need of actually implementing that average. So we'll start basically talk about methods, the different issues that occur within the definition of methods in Java, the fact that the values, the parameters are passed by value. We actually copy the value of the parameter when we send it to the method definition. But before we even do that, we have to understand what methods are useful for. So we start with the motivating problem. We want to find the sums of integers within multiple ranges. Like, I would like to have the sum from 1 to 10. I would like to have the sum of the integers from 20 to 30, 35 to 45, and so on. And one thing that we can observe here is that if we would write this program in basically what we wrote up to now, we would repeat the same code except some minor changes, like for instance, where do we start and where do we end, multiple times. And this is just if we want to actually compute this 3 times. But if we want to compute, let's say, the sum of numbers, the numbers between any integer up to any integer, we would actually have to repeat this operation many different number of times. But what we can see is that in all of these cases, we have exactly the same code. We define a sum equal with 0. We iterate with the variable I, the loop continuation variable, starting with 1, up to including the value of the upper range, like 10. We increment the sum with that value, after which we print the sum. And we would implement exactly the same algorithm again for computing the sum of the numbers between 20 and 30, and again between 35 and 45. We can actually abstract all of this by using a method. So the solution is that separately from the main method, we implement a method sum. This method sum is a public method, is available to any class, including the current class. It's a static method. We invoke it within the current class. In fact, everything that we cover this week, so up to next week, all the methods that we are writing are static. You see, the main method that we wrote up to now is static. The method sum is static. It's invoked separate, basically, by any class by using the class name, or within the same class by basically just calling that method from any static method. This method sum returns an integer. The third keyword that occurs in the definition of the method is the return type, followed by the name of the method, followed by the formal parameters to this method. These are basically parameters that are defined within the method itself. Then we have the code for that method. Any variable that you are using in this method, you should define it within the method, like we define sum equal with 0. For every I, an integer again, a local variable, starting with the value I1, the low range for this sum. As long as I is less than equal with I2, we increment the sum with the value of I, and the action after each iteration is to increment I with 1. The moment that I becomes equal with I2, we exit the for loop, becomes equal, we actually still sum it. We increment I2 with 1, it becomes I2 plus 1, which makes the condition false, in which case we return the sum. That integer will be returned as the value of the expression when we actually invoked that sum with actual parameters, with arguments that give values to I1 and I2. So internally what happens? During the execution of the main method, we encounter an expression or a statement that is an invocation to a method. Like in this case, we want to compute the sum of the integers between 1 and 10. At this point, we actually stop the execution of the main method and we pass the values. We copy 1 into I1, we copy 10 into I2, and we start a new frame, a new activation record for this method, which basically starts with the variables from scratch. We only have the parameters for this method and maybe some global variables that were defined within the class itself, not within the main method. So at this point, we compute the value of the sum by executing that method with the values of I1 and I2. And when we encounter a return statement, we actually stop the execution of sum. We return to the main method, we delete all the variables or the activation record for the method sum, and we return the value to the invocation. So in this case, it will return the sum between 1 and 10 and print that sum as part of the print statement. Again, next time we actually invoke the print statement, the first thing that it does, it invokes again the sum statement. So we are using the same method for all of these sums. We don't need to duplicate or replicate multiple number of times the same code. And that's actually the main advantage of methods. The fact that you can write once the code that solves the problem and you can use it over and over again as long as you need it. So why do we write methods? First thing is to make the program shorter and easier to understand. We see that here we had that snippet of 3 lines of code repeated 3 times. Now in the new method, we actually have it only once. The rest is the declaration of the method, which is necessary to identify that that is the method sum. It avoids writing the code twice or more times. And not only the important part is not the fact that it avoids writing the code twice, but if we made a mistake in the first case, now the mistake is duplicated if we are actually copying the code twice or more times. So when we correct that mistake, in fact, we will have to correct it in every occurrence of that code that was copied multiple times. In fact, almost 50% of errors that occur in computer programs are because of copying code from other locations without completely correcting it. So the rule of thumb of writing methods is, in fact, any code that is invoked at least twice, you should create a method for it. That way, it's only written once, and if it needs to be changed, maintained, corrected, debugged, we only do it once. It also will make your program more modular. Basically, we can test independently methods, and once we fully tested those methods for all the input values, we don't need to actually trace those methods. So part of the debugging issue that we actually talked at the beginning of this course is that we can actually skip the invocation of methods. If we trust that the method actually returns the value that is needed, we don't need to actually trace statement by statement within that method. We can directly skip that method execution and it will execute it and return the values or do the changes to the global segment of memory that need to be done. Writing methods, it would also make our program more readable. Now we can actually understand that in this case. What do? We print the sum and we invoke the sum that basically computes the sum of those integers. It makes the program easier to read for a beginner and even for large programs. We would not have to write methods that have thousands of lines of code because we can abstract pieces out into methods that are fully tested. It will make the program more reusable. Like for instance, now if I need in another program a method sum to compute the sum between two integers, I can directly use this one. I can invoke it with the class name, period, the method sum, and the arguments that I want to pass to this method. So once you write a method, if that method gives you some visibility modifier like public, you can use it from everywhere. And in fact, that's exactly what we are doing with the statements that the methods that we are invoking from the Java lang, the core of Java implementation. Like for instance, println is a method. Somebody wrote it from Sun. Sun was purchased by Oracle many years ago, and we are using it. We basically are invoking the implementation of that method. It will make the program easily testable, easier to test. Basically, once you test independently various methods, you can declare that these methods are correct. They don't need to be tested separately. Debuggable. Basically, once the program is tested, each method is tested, you can skip executing internally that method. You can just skip the method execution, it will execute because you trust that that method is implemented correctly. Extensible. We will see later when we talk about object-oriented programming that we can override methods. Basically, when we define a subclass, by default, we would also inherit all the methods defined in that subclass. But if we want to implement a specialized method, like for instance, we have in the superclass that we import a method toString. Like for instance, in the geometric class, we would have a method toString that prints, let's say, the color of the object and other features about the object, when it was created and if it's filled or not and so on. In a subclass, we can actually put more information, like in a circle, we can print the radius or maybe the area or the perimeter and concatenate this output also with the output written by the superclass method toString. So it makes it easier to extend already existing functionality with additional functionality. And finally, it will make it more adaptable. We can modify easily. We can actually write a wrapper method that invokes the old methods and also modifies some of the execution of the old method by basically assigning different values to variables and so on. So the rule of thumb, as I said earlier, is that if you have to perform any operation in more than one place inside your program, you should make a new method to implement this. Because there are higher chances that we are making mistakes when we copy and paste code from one location to another, instead of actually rewriting this, writing a method and invoking the method as many times as we need it, including from other programs. So today we are going to learn to define methods and invoke methods. So first of all, just to understand what a method is a collection of statements that are grouped together to form a single operation. So in this example, we are defining a method max that takes two integers and returns the maximum value between the two integers. And internally, this is implemented by defining a variable result. If number 1 is greater than number 2, it would assign to the result number 1, the greater of the two. Otherwise, it would assign to it number 2, and we would return that result. So the body of the method follows the method signature or the method header in a block. Now, the method name together with the formal parameters, the parameterized list of arguments to this method, is called the signature of the method. The signature of the method is also preceded by the return type, which is the return type of the values that we return, and other modifiers. The modifiers specify the visibility of the method. If this method is available to other methods in the same class, that would be a private method, but not to other classes. Or if this method is public, public means that the method is available to all classes in all packages. And finally, static. All the methods that we are going to write in this week are static. They basically take as take as parameters all the inputs necessary for the method, and the method can be invoked without having to create any object instance of the current class. We are going to understand what those are when we talk about object-oriented programming. At this point, we only have to remember the fact that all the methods that we are writing this week are static. Next, we can invoke a method, like for instance max, by passing it actual parameters. Actual parameters or arguments are basically values that get copied into the formal parameters. So when we execute the method, we have these input values. Finally, when we execute a method that returns a value, like for instance in this case an integer, we can use it in any expression. We can basically assign that integer to a variable of the type int. So the first part is really the combination of the method name and the parameter list. That basically gives us what is the method that we invoke, the name of the method like max, and what are the types and the number of parameters. So this is what is actually collected by the Javadoc, the API for a class. It basically returns the set of methods with the input parameters for these methods. In addition to that, the API also has the return type. It tells us what is the type of the object that we are returning. So, for instance, if you have any favorite class in Java, you can actually look for that class API. So for the class string, we can actually read the documentation, let's say for Java 9, to see what are the methods available for the class string. So this is the API. It basically specifies that the class string contains a character add method that passing an index, it returns a character. So from a string we can get a character. We can also get, let's say, the length of the string and so on. We can basically check each one of these methods to see what are the input parameters and what is the output, the return type, the return value type. Okay. So the formal parameters is really the sequence of parameters and their associated types, which are variables defined within the method header, and they are available within the method body. So once the method starts, we can use number 1 and number 2 as local variables. They will disappear the moment that we return the value or we return from that method. When we pass values, these values that are passed through invocation to the method, like we did in the sum method, they are called actual parameters or arguments. Java has a type of invocation of methods called call by value, which basically copies the values of the arguments, like for instance an integer, 2 integers in this case, copies the values into the formal parameters. So it will execute the body of that method with the values of the original actual arguments or actual parameters or arguments. The method may also return a value. Basically, in this example, we are returning the result, which is an integer. Therefore, the return value type returns integer. Such a return type value is required. So we basically, even if the method itself does not return a value, we must specify that the method does not return anything. And we can do that with the keyword void. And you have already seen that in the main method. The main method that we wrote for any one of our previous programs returns void. Basically, the main method does not return a value. When it finishes, it finishes. Now, one other thing is that you can still have a return statement in the main method. That will basically not return a value, will just be a return statement, which returns from any point within the execution. It could be part of the body of an if statement, in which case basically it returns from that method without having to execute the rest of the code in that method. Now, there is a word of caution. if the return value type is a type that is different than void, like for instance integer, string, or any other type that is not void, you must have on all the possible execution paths within your method body a return statement that returns a value of that type. So in this case, since the return value type is integer, we have a return result of the integer type on any possible execution workflow in this program. And why? Because no matter if the condition was true or false, we eventually finish the if-else statement, and this return statement will be encountered. So a return statement must be encountered on every possible execution path throughout your method. So what happens when we call methods? Basically, we are passing the values of the actual parameters or arguments to the values, to the variables that are the formal parameters, and we execute that new method on a new referencing environment, on a new set of variables that are available, which is basically the formal parameter parameters in addition to any local variables that we may have. So let's actually execute this little piece of code that basically within a main method it computes the maximum of 2 integers and then it prints in the main method those 2 integers. So we start the execution of the main method by defining a variable I equal with 5. Then we define j equal with 2. We have 2 variables available. And now we assign to k the value of the expression, which is a method invocation, maximum of I and j. But one thing that we said in the case of expressions assigned to variables is the fact that the expression is evaluated first. So now we need to evaluate maximum of I and j. I is 5, j is 2. So what happens is that we copy the values of I and j to the corresponding variables in the same order, num1 and num2, the formal parameters within that method. So we copy the value of I, which is 5, to num1, and of j, which is 2, to num2. And then we start executing separately that in the main max method. We define a result variable equal with 0. We check if 5 is greater than 2, which is true, and we assign 5 to result, and we return result, which will return back the value of that expression. And now we assign 5, the maximum of 5 and 2, into the variable k. So again, we do exactly the same thing that we did when we invoke the method. We copy the value of the variable result into the variable k, basically into the value that was requested for maximum of 5 and 2. So although result will be deleted the moment that we end the execution of the method, now that value was already copied in k. And we print that the maximum between 5 and 2 is 5. So again, what are the benefits of methods? We write it once, we use it everywhere. It also hides information, which is called encapsulation, and we are going to go into detail about what exactly we are hiding once we are actually doing object-oriented programming. But for the moment, what you basically have to understand is that it hides the implementation of that actual method from the user. Like for instance, when we execute a print statement, which is a method invocation in the Java core, Java system.out, we do not, which is a print writer, we don't actually go to see how is println implemented. We are just invoking it. The implementation of println is hidden from us. So we don't need to actually even to know how that method implements prints character by character in the output stream. It reduces the complexity for the developer by basically hiding implementation of methods that are already tested. It's known, it's very well known how it executes. So the set of methods that is available from a class or the application programming interface API is basically the set of all the possible methods, signatures that are available from a class. So the method body is like a black box. It can it may contain a very complicated implementation of the method, but really what we are interested in is the method header, or basically what are the methods that we can invoke from that class, and what are the type of arguments that these methods accept, and what is the type of the return value. And that's exactly what the API stands for, is the set of arguments for the input and the return value of the method. The implementation of the method is like a black box. If we know that it's correct, we don't actually need to know how is it implemented internally. And earlier this semester in the first lecture, you can actually see how to generate the Javadoc for a project. You can do it either from command line. There is a special executable called javadoc.exe on Windows, or just Javadoc on Unix-based operating systems, which will generate a package of HTML files or web files that basically contains this definition of all the methods that are generated for a given class. So for instance, everything that you see here, the methods that are defined for the class string, all of this was generated automatically from the implementation of that class in Java. And in the first lecture, I would advise you to go back to that lecture. If you have like a class or multiple classes in Java in the project generate Javadoc, you can actually generate the set of all the methods available in your classes. And the main file that it will be created is the index.html that contains links to all the classes and their internal API for Javadoc. And you have screenshots with where to find that in the lecture notes. Okay. Now, earlier today I said that if you require to return a value, the return value type is different than void, it is required that we have a return statement for every possible execution path in the program. So for instance, let's take a look at the program on the left hand side. During a compilation time, we do not execute conditions. Even if conditions are always true, or if conditions are selectively true, like for instance, in the range within the value there are no other possible options, the compiler does not execute those conditions. So all that it does during compiling is to check that on all the possible execution paths for that method, we have a return statement that has a value or an expression of the same return value type with the signature of the method, with the header of that method. So let's assume that the first condition was true, there is a return statement. If the condition was false, we go on the else statement and we check again. If the condition is true, then there is a return statement with an integer. Else, if the condition is true, we have a return statement, but what if this condition was false? So the Java compiler does not actually check the fact that there are known integers that are not greater than 0, not equal with 0, and not less than 0 at the same time. So in Java, if we write this method exactly in the way that we wrote it here, in fact it will tell us that this contains a compilation error. And that compilation error is that we do not have a return statement in case that this condition was false. So really we should write this program either by deleting the last if statement, because we know exactly that only other possible case is that we want to return negative for negative numbers, or we add an additional return statement that it should never be reached. So it will be just a return statement that returns randomly 0, 1, or -1, or it returns, or it throws an exception. Later this semester we'll talk about exceptions. Basically they are alternative outputs or alternative return values from a method invocation. In our case, the easiest solution is actually to delete the last if statement. Basically the only other possible case is that n is strictly less than 0. Therefore, we tell the compiler, if you actually continue the code on the else branch, the only other possible case is that we reach a return statement to return -1 for the entire method. So there are 3 different execution paths, and on each possible execution path we have a return statement that returns a value of the same type with the return value type. Let's see if there are any questions in the chat. Yes, so the first question by Christina is that you can have as many methods in a class as possible. And in fact, the order of the methods does not matter. So for instance, let's assume that in our main method, let's create a new class, or we are reusing the test class. So this is our main method, and let's say that we have a system.out.println statement that prints the result of maximum of 4 and 7. And now we define the method maximum. Public, static, integer, maximum of 2 integers, integer x and integer y. And now we have an if statement. If x is greater than y, then we return the bigger one. We don't need an else, because the only other possible case is that we return y. So even if we put our max method after the main method, we still know that there exists a max and it will print the maximum. We can also put it before the main method. That will also compute correctly the maximum and return it. Okay? Any questions? So you can put it before and after the main method. The scope, or basically the amount, the program where this method is known, is the entire program. The order of methods in Java does not matter. So you can have it before the main method or after the main method, and the program is basically the same. There is no requirement that you have to put the main method at the end of the class, or you need to define the main method at the beginning of the class. You can put it everywhere you want. There is a style that people put the main method at the end of the class, just because it's a common convention that if you are looking for a main method, you should look at the end of the class. But there is no such requirement. Okay, so let's continue. Now, methods are executed independently from their caller methods. Basically, the methods that were called that called the current method, the parent method, let's call it. So, for instance, when we execute the main method, we have a set of variables I, j, and k in the order from bottom to top of the order that these statements for declaring these variables were executed. The moment that we invoke another method, we create on the stack a different space of variables, a different set of variables. These are called frames in programming languages, or activation records. Basically, it's a set of new variables that are available for this method execution. So we copy, for instance, in this example, the values of I and j into the variables formal parameters num1 and num2, and then we start executing the method max independently from the space required by the main method. So in fact, we cannot use, during the execution of the max method in Java, the variables I, j, and k. These are variables that are local to the main method, although in this moment we are actually executing the method max. We cannot access I, j, and k. These are hidden because they are in a different activation record. We execute the method max, we compute the result, and we return that result. At that moment, we return the value that was computed to the variable k, and we pop from the stack the activation frame, the activation record or frame of the method max. So we return to the previous set of variables, the variables that were available in the main method. Even in the moment that the main method terminates, it actually gets the activation record for that main method gets deleted, and when we finish executing programs in Java, the stack is finally empty. So stacks are basically like pyramids. You can put on top of the stack new activation records with their own set of variables. You can only take or remove these activation records from the top of the stack. It's basically one data structure that we will see later this semester. In fact, we will see next class, where you can only push new elements on the top of the stack, and you can remove elements from the top of the stack. Basically, the last element that was inserted is the first one to go out. In fact, that's another shortcut for stacks, LIFO, L-I-F-O, last in, first out. So let's see what exactly happens when we execute the previous program on the stack. So first we have the main method activation record, which basically contains initially no variables. But once we start executing the statements, we can define variables like I is declared and assign the value, initialize with the value 5. J is declared, is actually stored on the stack on top of I, is the top of the stack, empty. Then we invoke the method max, and the method max creates a new frame on the stack. So basically we have a new activation record, a new set of variables. Initially we only have the formal parameters, and these formal parameters in Java take the value of the actual parameters. So we basically copy the values of I and j into number 1 and 2 respectively. Then we start executing the max method. So we allocate space for the result local variable. We execute the conditional statement if number 1, which was 5, is greater than number 2, which is 2. That's true. So we assign 5 to result, and we return the result. We basically copy the result before we delete the activation record or frame for the max method. We copy 5 into the value of k. At this point, we delete the frame or the activation record for the method max, and we print the maximum in the main method. At this point, we are already back in the main method, so we have access to I, j, and k. Within the method max, we really could not access the variables I, j, and k. Which brings us to the type of call that Java has, and it's called call by value. Basically, the formal arguments inside the method are copies of the original data. So the consequence of that is really that if you are assigning anything new values to primitive formal arguments, the formal arguments of a primitive type, you are affecting the local formal arguments, but you do not affect the original past variables. So the cannot is really applies to basically both statements. You cannot assign new values to the formal parameters and also affect the original variables that passed. Why? Because the changing argument values changes the copy, not the original. And I always found that it's very useful to actually see this through an example. So let's assume that we are returning to our previous program where we have a main method. Inside the main method, we define some variable, let's say x is equal with 5. Then we invoke a method m with x. And we print the value of x. In the method m, which is defined after the main method, takes an integer, let's call it copy of x, we assign a different value to copy of x, maybe 10. So we defined x, we called the method m, which took a copy of x, so copy of x is 5. Now we assign to copy of x 10, we exit the method m, we return here, and we print x. X is still 5. Why? Because we modified the new variable copy of x, but we never reflected it back in x, because x was just copied unidirectional from the main method, the invocation, to the actual definition. And here, this is a totally new variable, it doesn't reflect back to the previous variable in the main method. So basically, when we copy values, like we copy actual arguments, num1 and num2, into local variables n1 and n2, no matter what we do with n1 and n2, we can modify their value, that is not reflected back, because we only pass unidirectional into basically one direction from the actual arguments to the formal parameters inside the method. Even if we try to swap the two variables with a temporary variable, that will not swap the two values in the main method, because in the main method the values are still the same, the original ones. Okay, next, overloading. So sometimes we need to define multiple methods with the same name. Like for instance, the previous method that we defined, max, was working for two integers, and it would return an integer that is maximum between the two. But it would be very natural to also define a method that takes two doubles and returns the maximum, or a method that takes, let's say, two strings and returns the maximum in lexicographical order of comparing the two strings. So it's very useful to define the same method name, but with different implementations and different input parameters. Like for instance, the difference between these two methods is that when we invoke the methods, we know exactly that we invoke them with two integers, or with two doubles, or with a double and an integer. If it's with a double and an integer, we cannot actually invoke the first method, so it will always raise basically the integer to a double, so it calls the second method. This overloading of methods in programming languages is called overloading. We are overloading the name max or any name of a method that is defined multiple times for different types of inputs. However, it has a side effect. Sometimes it may be ambiguous which method we are invoking. So let's assume that there are two or more possible matches for the invocation of the method, and the compiler cannot really determine which is the most specific match. This kind of invocation is called an ambiguous invocation and is a compilation error. And here I give you an example. I define two max methods. Both max methods take an integer and a double, or a double and an integer. As long as I don't invoke these methods, or I invoke them with an integer and a double, or a double and an integer, everything is fine. However, if I try to invoke that method with two integers, I can actually invoke both methods with equal transformation. In one, I would transform the integer 2 into a double. In the second one, I will transform the integer 1 into a double. So neither one of them is basically better match for the invocation of max of 1 and 2. So the compiler basically makes a decision that they are both equally far from the method max. So if this code will basically give us a compiler error, because Java, and in fact any other programming language that relies on basically calling a method with basically types that are equally far from the arguments, it's impossible to decide if it's better to call this max or to call this max. So usually when we do method overloading, we have to be aware of this kind of errors. When we actually try to invoke a method, but that method is equally far from basically multiple definitions of the method. And that's basically ambiguous invocation. Okay. Now, any local variable that is defined within a method is called a local variable. Basically, the scope is the part of the program where the variables are referenced, which in Java is from the beginning of the declaration within the body of that method up to the end of the block in which that variable was defined. So local variables, like for instance integer x. Integer x disappears at the end of the method. Moreover, you cannot redefine the integer x neither within the current block or within inner blocks. Like for instance, in this method block, we have an integer x equal with 1, and we redefine the integer x inside the for loop inside this method. This will actually result in the compilation error. You cannot redefine a local variable. A local variable is available within your method, between where it was declared up to the end of the block in which that method was declared, but is not available anywhere else. Basically, it will be automatically deleted at the end of the block, and you cannot redeclare it. You cannot declare x again within the method max, even correct method, even within an inner block. Now, there is actually a typo in this method. This is an incorrect method, not really a correct method. Okay, I will make this change in the lecture notes later. So the scope of method abstraction is really that we actually define problems, solve problems by employing an algorithm called divide and conquer. When we write a large program, we try to decompose that large program into sub-problems. Like for instance, in this example, print calendar, we want to print a calendar. Given a full year and a month between 1 and 12, this is actually part of your lab, we would like to see the calendar for that specific month, like 2009 April. Okay? We can decompose this problem step by step, either in a top-down fashion, or we can compose this problem in a bottom-up fashion. Basically, what are the pieces that we need to implement in order to implement the total, the complete implementation. So here, basically, we want to implement the print calendar, or the main method of this program. It has two parts. If you look at the program, it has reading the input and then printing that specific calendar. And then each one of them may have lower parts. Like for printing a month, we have to print the title of the month or the header, and then the body of the month. And for the title of the month, we have to get a string representation of the month name from the integer representation. And for the body of the month, we have to get the day within the week, the number of days in the month. We should check if the year is a leap year. And we basically can implement it in two ways. Once we design how to implement that specific problem, we can implement it top-down. That means that we start with the implementation of calendar, and instead of calling methods, the read method and the print method, we can actually just basically ignore some of the methods or use comments to comment out the parts that we are not currently implementing. That is basically the top-down approach. We implement one method in a structure chart from top to bottom. We start with the most important method, and we use invocations to methods that are empty or return some type of default value. For an integer, it returns 0. For a string, it returns empty string, and so on. Those kind of methods that are not yet implemented are called stubs. They are basically simple, correct, but incomplete versions of the methods. They are used for basically those methods that are not yet implemented and will be implemented later. like for instance getting the start date within the current month, like is it a Monday, is it a Tuesday, Wednesday, and so on, we return a default value like integer 1. It's a dummy value, but it will do for testing the methods above the current method. So the use of these stubs will let us test that method from the caller, and actually to test independently the caller from the lower level or children methods. So we implement the main method first. The main method will use stubs, basically calls or invocations to empty methods to call the printman method. Then it implements basically the printman method, which calls the get or print the header also as a stub, and so on. The second approach is called bottom-up approach. That means that once we implemented the hierarchy with stub methods, basically we have this hierarchy of empty methods. The method print calls read and print, but these are empty methods, or they actually call the children methods like print month title and print month, and print month title gets the month title. We can start implementing these empty methods from the bottom to the top. So that is called the bottom-up approach. We start implementing one method in the one by one, the methods in the structure chart, from the bottom methods to the top. For each implemented method, we can actually write independently a test program to test that one method and basically decide when that method is complete and correct. Both methodologies for implementing methods are fine. Basically, in the end, they result in a correct program. One that is maybe developed from the bottom or one that may be developed from the top. It depends on the programmer. It depends also on the style that is used. Most of the time, we are using them together. Like we start with defining the chart, the structure hierarchy from top to bottom, and then we implement the methods from bottom to top. The advantages of stepwise refinement is that it simplifies the development of the program. You don't have to remember everything that is in the program. You can only implement these simpler methods one by one. Yes, the program may be very complicated, but if we implement step by step sub-problems, then it basically results in implementing the entire program in an easier way. It's an easier development, debugging, testing, and it also facilitates teamwork, because now you can actually assign different developers to the different parts of our programs. So let's actually do an example with this development, this style of development. And since the previous example that we did was part of the lab, we should probably implement, let's say, one problem from the homework. Let me check which is a method that would require some kind of method declarations. Prime numbers. So for the prime numbers program, we want to write a program that a method is prime that takes an integer n, and an integer greater than 1 is a prime number if the only divisors is 1 or itself. For example, prime of 11 would return true because 11 is only divisible by 1 and 11 within 1 and 11. Prime of 9 is false because 9 is divisible by 3, which is different than 9 and 1. We want to use this prime method to find the first 1000 prime numbers and display every 10 prime numbers in a single row, as basically follows in the next example. So in this problem, we basically need methods. We need a method that checks if a number is prime, and we need another method that basically iterates over numbers until it finds 1000 prime numbers. So let's create a class for this program. Let me actually also clean the test program. So this is part of the homework. You are free to use what I actually write in the program and record online. The name of the class should be prime numbers. It should contain a main method. And the only output for this program is basically to print the 1000 prime numbers. So let's start with top-down development. So the program should print the first 1000 prime numbers. We are going to do that as a method. So public static void first 1000 prime numbers. Let's leave it empty for the moment. We are going to do now a bottom-up development. We need a method public static boolean is prime, which takes as an integer a number n and returns true or false if that integer is prime or not. So we can do this with a for loop or a while loop. We can actually iterate with a for loop. Let's start with a for loop. For every integer I, if starting with 2, as long as I is strictly less than the integer n, I is incremented with 1 after each iteration. We can check if the integer n modulo I is equal with 0. If n modulo I, the remainder after the division of n with I is equal with 0, then we return that the number is not prime, so we return false. Otherwise, we return true. So now we did the bottom-up development. Basically, we implemented the prime method. Now we can implement the first prime numbers. So let's start with defining a counter variable. Initially, we have no prime numbers. Then we should write an initial integer I, the variable that we start with at the beginning. And as long as the counter is less than 1000, we should check if the number is prime number. 1 is not a prime number. The definition of primes is a little bit vague about if 1 is prime or not, but I will basically start with 1 is not a prime number, so I will be incremented with 1. And then we basically need to check if the new number is a prime number. So if is prime of I is true, then we actually should increment the counter. We should print the value of I, and we should concatenate that with a space. And then optionally, if the count is divisible with 10, then we should also concatenate it with a new line character. Otherwise, we basically just have an empty string. Okay, so now we can run the program, and here are the first 1000 prime numbers: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. These are exactly 10, and then the next 10 prime numbers, and the next 10 prime numbers, and so on. So the complete method is actually developed here. We basically developed top-down. We needed a method first 1000 prime numbers. We left it as a stub. Then we implemented the base method is prime. Then we implemented bottom-up the first 1000 prime numbers, and we have the complete program. So let's record everything and post it on